Hi everyone, Mahmud. I'm research assistant for Maria. So I'll be discussing our recent work on assessing the reasoning capabilities of LLMs in context of evidence-based claim verification. So in quick summary, we created a benchmark for claim verification that had the task of claim verification using three different
If
data
you're
sets.
advancing the slides, we're not seeing it.
I'm just giving a quick
Okay,
summary.
okay, okay.
So yeah, in this work, we basically created a benchmark based on for claim verification based on evidence, and then we evaluated LLMs on reasoning capabilities specifically for deductive and abductive. So let's see reasoning. It's quite relevant now for many different reasons. DeepSeek came out with R1 and that tanked NVIDIA stocks. So yeah, everyone wants reasoning in their models. So it's the process of drawing conclusion from a set of evidence via inference steps. And obviously, it's like essential for many different tasks, and it improves faithfulness of model rationales that's required in many different fields, like timeline summarization, long context QA, fact checking, hypothesis generation, etc. And obviously, with good reasoning, we can reduce hallucination, and good reasoning also helps align model outputs the way we want. And it definitely is useful for adapting to dynamical settings of real world tasks like messy social media data. So let's first see some failure cases here quickly. So I'm going to start with a bit high level case of some visual reasoning that I found recently. So if you go to GPT-4o and if you ask it to generate an image of an empty room with absolutely no elephant, it generates this. Then if you ask it, do you think the image has an elephant in it? It'll say, nope, the image has no elephants, just an empty room, as requested. If you suspect otherwise, let me know what you see. So moving on, more failures. What is the last word in this question? Asked to R1 distill Quen 1.5 billion. This is a big enough model, small but big enough, 1.5 billion parameters. It fails to answer it. What is the last word in this question is that. Moving on, this is more specifically for our use case. We have a claim about German wing crash. The claim says 148 people were deceased, whereas the evidence is stating that 150 people were deceased. So obviously the veracity is refuted. But if we see the rationales of the LLMs, so these are all with manual code prompting, GPT-4, GPT-4o, and Claude V3 Sonnet. GPT-4 says evidence supports the claim, whereas again, 150, 148 doesn't support, should be refuted. GPT-4o says evidence supports the claim. Claude says evidence confirms a similar total number of casualty. So none of the models in their rationale says that no, evidence explicitly refutes the claim. So this brings us to the question of evaluating these LLMs for more, like real world data sets instead of just evaluating them with coding or math questions. Those kind of benchmarks are using MMLU for the nth time. For that, we came up with this benchmark. But before I go on to the benchmark, let me explain our framework that was used to create the benchmark. So we came up with a logical reasoning framework. RECV is reasoning for evidence-based claim verification. So the logical reasoning framework is to have a more uniform taxonomy in order to annotate data, because in our um, background work we found that yeah, everyone calls some reasoning something else in some capacity. So how this framework works is we break down what is what. So these are our most lowest and primitive level of reasoning. It's deductive, abductive, inductive, and analogical. Deductive is when you can come to a conclusion directly from the evidence. Abductive is you need to generate some form of hypothesis and then get, like, choose the best hypothesis. Inductive is when you have a set of evidence and you need to come up with a conclusion that's more generalizable beyond your set of evidence. And analogical is when you have entities that are similar and you compare them to come some sort of conclusion. So these are our lowest level reasoning types. And then we get compound types. So the main idea behind compound type is these will be concatenation of our atomic types. So let's say causal, it'll probably have a combination of different levels of deductive and abductive. So compound comes from multiple atomic together. And then we can scale up more, go up to composite task. These are absolutely more abstract and complex reasoning tasks that encompass everything that's on the left. So you can have multiple compound types like causal, temporal, common sense for legal reasoning, social like neural theory of mind, communication, and game theory stuff, medical combinatorial. And so these are the reasoning types we first define. And then the other thing is the process. This is outside of our reasoning types. Process can be multi-hop reasoning, counterfactual, or fallacy. So these, like, you can have multi-hop in any three of these. That's the main idea. Your atomic type can be multi-hop, compound type can be multi-hop. So this is the reasoning framework we used to annotate our data sets. So let's see how this can be used. So if we have a claim and evidence, so our reasoning task is claim verification. Our process is obviously here single step, and our type is atomic. Here we'll be only using abductive reasoning. Here we are talking about Pluto's climate change over the last 14 years is likely a seasonal event. The evidence is given for Neptune, and we are making a plausible hypothesis that Pluto comes after Neptune, has a longer orbit, so most likely has similar attributes to Neptune. And the reasoning type is abductive, and we say like the veracity is supported. One thing to consider, abductive reasoning, like the conclusion can be false. So there's that issue. So we can be wrong here, but yeah, this is our best hypothesis within the evidence we have. So this is how you can get what the reasoning type is for a claim, evidence, and veracity label tuple. So how the annotation was done is we gave claim, evidence, and veracity to annotators, and then based on our guidelines, they chose what type of reasoning that was, deductive or abductive. So we only found deductive or abductive in the data sets. So those are the two reasoning types we cover here only. Moving on, then to the task definition and experimentation settings. So as I said, this is claim verification based off evidence. So if you have a claim like schools closed, residents told to stay indoor, then the evidence is like school went into lockdown, town appealed to residents to stay inside, then the LLM should provide some type of rationale like evidence mentions this, thus we logically conclude rumor is true, and the veracity. So this is how the task is defined, and this is how the LLM should reply. So yeah, claim verification is set up as a classification task where the model predict whether a given claim evidence pair is true or false. So the only two level we have are true or false. And we evaluated three different prompting styles: zero shot chain of thought, and manual chain of thought. For manual chain of thought, we had around 6 to 7 examples for each of the models, each of the data set. And our benchmark has 3 data set. I'll come to that soon. And we evaluated LLMs under 2 settings. These are explanation and no explanation. So explanation is when the LLM needs to provide a rationale first, then provide us the veracity. So it'll give us a rationale, then provide us a veracity. And for no explanation, it's just the veracity. So, and we evaluated Claude, GPT-4, and GPT-4o. This is the data sets within the benchmark. We have vitamin C, climate fever, and sorry, there's a mistake here. That should be FEAM plus. So vitamin C is the data set of the data domain is Wikipedia, where we have simple claims and evidence. with some evidence and claim pairs that are adversarially generated. Climate fever is the claims are from internet, real world claims, but the evidence is from Wikipedia and it's specifically for climate science. And Theme Plus, it's the claims are from Twitter regarding events, real world events, and the evidence is from news. So result wise, um, the models were evaluated based on F1 score, but we then had the implicit analysis of how many errors were deductive and abductive. We are mostly going to look here in the error rates of deductive and abductive. So first, let's see the error level between deductive and abductive. If you see, like, most of the error of deductive is much lower than abductive. In most cases, abductive error rate for all the data sets is almost 3 times on average. So yes, that's the first takeaway. Models are absolutely horrendous when it comes to abductive reasoning. And one of the main reasons we found was that models do not like uncertainty. They would rather say something more concrete than say something, than make a guess. And the other interesting thing we found was that there was no single prompting method that was universally giving us good results. So if you see, like, here, the bold letters are the best results, and a lot of them are within no explanation. So models did better and had lower error rate when they just predicted zero shot, did not provide any rational. Whenever they provided rationals, for vitamin C, providing rational improved deductive reasoning, but it was mixed for abductive. For climate fever, providing rational always reduced error rate. So yeah, whenever you wanted a rational from within climate fever, the models would perform worse. For Fame Plus, deductive went up a bit, but abductive mostly went down. So that's the thing. Rational generation impacts performance, and performance of reasoning capability also depends on your data domain and task complexity. For instance, vitamin C is much more easier than climate fever, and climate fever is relatively easier than Theme Plus, because this vitamin C and climate fever data domain is Wikipedia, whereas Theme Plus is real world news. Then we also evaluated the rational qualities, the rational generated by the models. We used evidence appropriateness, factual consistency, BART, and perplexity. The main takeaway here is that models usually generate faithful rationals. We had ground truth from our annotators. That's how we got this evaluation. So yeah, the rationals were faithful enough, but the quality was much better when the prediction was correct compared to when the prediction was wrong. Here we are just providing the macro results. And here, like, MCOT on average provided the most consistently good rationals. So in conclusion, the main findings are LLMs are good with deductive reasoning but cannot perform abductive reasoning. Reasoning capabilities vary depending on data domain and task complexity. MCOT doesn't always work. Specifically, there's no specific or universal prompting that we can use across all data set and task. And lastly, yes, LLMs are somewhat capable of generating faithful reasoning rationals. Um, that was our work. Thank you. Please let me know if you have any um, questions. This is our paper.
Thank you very much, Mahmud. Other questions? Okay. Is there one person online? Yeah. Would you like to unmute yourself and ask your question?
Yes, hiya. Thanks for that. It was really very interesting. I just wondered about the, I'm not familiar with the data sets that you use for evaluation, Theme Plus and the others. And I was wondering, I get the impression that because you presented the F1 score, that it was a binary metric. But as you said, sometimes they can be quite complex. And even in the sort of first task that you showed, where it was one of the examples where it's sort of 142 people have died or 150 people have died, you can sort of imagine that there is some room for interpretation, maybe not exactly in that task, but in other tasks, about whether something is true or false. And I was wondering, having seen the examples in the data set, do you think that there's ambiguity in some of the examples which might affect evaluation, or do you think they're all relatively clear cut as definitely true or false?
So there might be some ambiguity with Theme Plus because it's real world claims from Twitter and social media, and the evidence is obviously news and events fold over time. So how the evidence is coming out and when we're collecting the evidence can have some ambiguity within them. We try to minimize our ambiguity with how we selected the data sets. Apart from that, for vitamin C and climate fever, it should be more straightforward and concrete, especially for vitamin C. There shouldn't be any ambiguity in vitamin C.
That makes sense. Thank you.